Hello, Math 201. Welcome to today's lecture on section 5.2, definite integrals. So this is, if you remember, we've learned about indefinite integrals. And so those are when we have something like f of x, dx like that. But we're going to learn about definite ones where we add bounds to it. And it's going to end up being that definite integrals are actually going to be exactly the thing we want that calculates the exact area under a curve. And then also for the homework, just know that to save time, using a Riemann sum calculator will be very helpful with just kind of calculating some of these things. So you're allowed to use it for the homework. For the quizzes and the exams, you won't need to use it. So for the homework, use online Riemann sum calculator for the homework. Okay. So remember last time that we learned about Riemann sums, where it's the sum of a bunch of heights and widths, and this is the area under a function on a given interval from a to b. But what Wade never really said, but it kind of was assuming, was that f of x was always positive. It's always positive area. But now we're going to talk about what happens when f of x is negative. Does this definition still make sense? And it turns out it does. And so we're going to show what that actually means. And so I'm going to do this rather quickly. So we're going to do the midpoint Riemann sum for this function on the interval 1, 3 with 4 rectangles. So 4 rectangles on that interval means each interval is going to have width 1 or 0.5. And then the intervals are going to be 1 to 1.5, 1.5 to 2, 2 to 2.5, and 2.5 to 3. So the midpoints of those are 1.25, 1.75, so on and so forth. So that the midpoint is just the width, 0.5, and then f evaluated at those values. If you plug those guys into this function, you get this, and this would be a totally fine, reasonable answer on an exam. And this number is negative 6.625. So how are we supposed to interpret that? What does negative area mean, right? Because we've really only talked about area, and we've never really thought of negative area, just positive area. So what is negative area? And this picture kind of shows what negative area is. The function is below the x-axis. So all these function heights are technically negative because they're below the x-axis. And so this is approximating the area between the x-axis and the curve. And when it's below the x-axis, it's negative. And so that's what this negative 6.625 is. And then if you do the left Riemann sum with the same points, so it would be 0, 0.51, 1.52, and 2.5 with 6 intervals, and plug it all in, you get negative 3.875. And so again, this is what this picture looks like. So now when we do the left endpoints, it's that green one, 0, negative, negative, negative. And so what the Riemann sum is, it's the net area. It's the positive area subtracted by the negative area. And so it tells you what the net area between this curve and the x-axis is between that and that. And so that's what a Riemann sum tells us. A Riemann sum tells us net area, where negative area is area below the x-axis. So this is what a Riemann sum looks like when we're below the x-axis. It's red, it's negative area. And then area above, we'll call it green area. And so the Riemann sum from a to b for this function is that area plus that area minus that area. So it tells us net area. So what that means is, like, for instance, if you have negative velocity, you're going in the opposite direction. And so the net area would be your total displacement, right? Because you went in the positive direction, then you went backwards, then you went back in the positive direction. And so it would tell you where you ended up. Whereas if we brought this up here and then just did total distance traveled, making everything positive, that would be total distance traveled. And so net area is going to be the sum. It's going to be the parts of R that lie above the x-axis minus the sum of the areas that are below. And so that's what net area is. So that's what net area is. And now we're going to talk about what happens when we take the number of rectangles and make it go to infinity, and how that's going to give us the exact area. And we're going to define that. We're going to give that a name, and that's going to be called the definite integral. The idea of a definite integral is take a Riemann sum and then let the partition, the number of rectangles, go to infinity. If you let the number of rectangles go to infinity, it becomes better and better approximation until it's basically the exact area. And so that's the idea of a Riemann sum. A definite integral. A definite integral tells you the exact area under between the exact net area between a curve and the x-axis. And the way we define it is by taking the limit of the number of rectangles in a Riemann sum as they go to infinity. And so I'm going to skip some of this technicality stuff. It's not that important. The idea is that we actually technically need to build this for any partition, but it's really not that big of a deal. And so if you want to read it for kind of posterity's sake, that's fine. But what we really need is this definition. So the definite integral. So a function defined on a closed interval is integrable on this interval if, and so they say the limit is delta goes to 0. Really, that's the same thing as the number of rectangles going to infinity. And so that's what I'll normally use because it's simpler. Is unique over all positions and all choices. This limit is the definite integral. So when you take the limit as the number of rectangles goes to infinity, that area is the definite integral of f from a to b, and we write it like this. The integral from a to b f of x dx, this is the definite integral, and it's the limit as n goes to infinity, the sum from k equals 1 to n of f of x or x sub k star delta x. And generally, this could be for any Riemann sum. And so we generally pick the right Riemann sum because it's the easiest one to do. So in other words, the integral from a to b of f of x dx is the exact net area under f of x on AB. And note that this is a number because it's an area, right? So it's going to give you a number. Notation-wise, where does this come from? This elongated s is supposed to kind of be taking that sigma s and stretching it to let you know it's kind of a sum. This is what's called the integrand. This is the upper limit of integration, the lower limit of integration. And then this is the lower limit of the summation, upper limit of the summation. And so this dx comes from this delta x, right? Because it's an infinitesimal width, because we're doing a bunch of heights and infinitesimal widths and adding them up. So that's the idea. X is called the variable of integration, often called the dummy variable. And dx, again, is an infinitely thin rectangle. The idea is that as you take this and chop it up thinner and thinner and thinner, the width of our rectangles are going to 0. And so that's what this little dx stands for. It's reminding you that the width is infinitesimal, or it's like infinitely thin. Okay, and note that what the variable is does not matter, right? All three of these things are the same area as long as that x matches that dx, that omega matches that omega, that s matches that s. They're all representing the same area. And so that's why it's called the dummy variable, because this is just a number. And then there's a really nice way to know if a function is integral, like whether or not you can calculate this sum. And if f is continuous or bounded with a finite number of discontinuities, then f is actually integrable. And the proof of this is well beyond the scope of the class. But if you're a math major, you learn about this in real analysis, which I'm teaching in the fall. And so this is something we'd actually learn on the proof of this. And it's actually quite cool. It uses these very technical terms, and it gets into the beauty of what is actually happening at infinity when you do something like this. Anyways, let's talk about how to identify the limit of a sum. So assume that I give you this Riemann sum, and I tell you that this Riemann sum represents some definite integral. And so is the limit of a Riemann sum for a function f on a closed interval 1, 3. We want to identify the function and express the limit as a definite integral. What does the definite integral represent geometrically? And so remember that this limit, by definition, is the integral from a to b f of x dx. Since our interval is 1 to 3, a to b has to be 1 to 3. And so that's going to be a and b. Because this is f of x k star, then f of x must be 3x squared plus 2x plus 1, right? Because if you plug in x sub k star right there, you get that, which is that right there. So that means f of x is 3x squared plus 2x plus 1. And since the interval is 1, 3, a must be 1 and b must be 3. And so this must represent the integral from 1 to 3, 3x squared plus 2x plus 1 dx. And geometrically, what that represents is it is the area under the curve from 1 to 3. So this integral right here, this definite integral represents this area, which is the limit of the Riemann sum. So if I wanted to actually calculate this area, I have to right now, we're going to learn a much better way soon, but for now, we'd have to actually calculate that limit. So in order to calculate this particular area, I need to calculate this limit, which is kind of annoying. It's doable, but annoying. And so right now we're going to, instead of evaluating this to find the limit or to find the area, we're going to use geometry, right? If this was a nice like straight line, then this would be a trapezoid and we could just use geometry. And so what we're going to do is we're going to do exactly that. We're going to do definite integrals using geometry. So we're going to use familiar area formulas to evaluate the following definite integrals. So for instance, 2x plus 3, if you graph that function, it's a straight line starting at 3 and going up. and we want to integrate it from 2 to 4, so from x equals 2 to x equals 4. And if you did that, this area ends up being this trapezoid with height 7 here and height 11 there and width 2. And remember, the area of a trapezoid, if it has base 2, base 1, and height, is 1/2 base 1 plus base 2 times height. And so the area is going to be 1/2 11 plus 7 times 2, which is 18. So that this integral right here, which is this area, is equal to 18, just by using the area of a trapezoid formula. Now let's do the same thing for this guy. If you graph him, the line looks something like this. We're doing it between 1 and 6. If you plug in 1, you'll get -4. If you plug in 6, you get 6. And so that's the height there. This height is 3, or that was 3, that was 2. And so it's going to be the area of this triangle plus the area of this triangle, but this area is negative. So the area of this first triangle is 4. The area of 2 is 9 by just using the area of a triangle. And so this integral is just going to be a2 minus a1, which is 9 minus 4. So the net area is 5, and it represents this area minus that area. And then finally, let's do this guy. So the area of the square root of 1 minus x minus 3 squared, it's going to be pi over 4, and I'm going to show you where that comes from. So this graph might not look familiar as it's written like that, but if you square both sides, you get y squared equals 1 minus x minus 3 squared, and then you add this over to the other side, and you get y squared plus x minus 3 squared equals 1, which this is a circle of radius 1 centered at 3, 0, right? So you go to the point 3, 0, and then you do a circle of radius 1. That's what this graph is right there. And so because it's the top part of it, it's just the top part. And so the area that they want from 3 to 4 is this little area right here. And so an area of radius 1, the area of a circle of radius 1, sorry, is pi, right? Because pi r squared. And so it's a fourth of that, so it's pi over 4. So this definite integral is pi over 4. And if I want to do, for instance, the integral from 2 to 4 square root of 1 minus x minus 3 squared dx, well, that would be this whole area. And so that would be pi over 2. And so that's another geometric shape that we know how to use. So we know how to do trapezoids, we know how to do rectangles, obviously, triangles, and we know how to do circles. So those are the ones that we can use geometry for. All right, let's talk about how to use definite integrals to kind of calculate some stuff. So here's a graph. They tell us that's A, B, C, and D, and they tell us what these given areas are. And so the integral for A, the integral from A to B of f of x dx, that is just this area right here. And so that's just equal to 12. For part B, the integral from B to C of f of x dx, well, that's going to be this area. So it's going to be -10. For part C, the integral from A to C of f of x dx, that's from here all the way to here. So it's that minus that plus that. So it's 12 minus, oh, sorry, we're only going from A to C. So it's just 12 minus 10. So the net area is 2. And then finally, part D is the integral from B to D f of x dx. And so what's the net area from here to here? Well, it's that area plus that area. So it's equal to -10 plus 8, which is -2. And so that's how we can do one from a graph. And then some properties of definite integrals. So these are just going to be definitions. If you reverse the order, so normally we go from A to B, but if you go from B to A, that's going to be the opposite. So we're going to define it as -A to B. So reversing order puts a negative sign in front. And if you do from A to A, so those two things are the same thing, then it's 0, right? If you have no width, then the area is going to be 0. And then also you can break up subintervals. So if I go from A to B and there's a point P in between, then the integral from A to P plus the integral from P to B is going to be the integral of the whole thing. And then so that means we could subtract off, right? So if I want to know what the area of just this little bit is, I could take the area of the whole thing and subtract off that area. So that's why the integral from A to B, from there to there, is the integral of the whole thing minus this little bit right there. Some other properties, this is by definition, this is also by definition. Remember, we can add or subtract integrals. We can pull out constants. So all those things from indefinite integrals still work. And then we can split up areas. And then the integral of an absolute value function. So this is important. So for instance, if we had a function like this, I had a negative area and a positive area, the integral of the absolute value function is instead you add the area of the positive. So you make this R1, you make it positive and add it to R2. And so it's the sum of the areas of the regions bounded by the graph and the x-axis. So you take instead of subtracting areas, you just add areas. So let's use properties of integrals to calculate some stuff. So let's say we know that the integral from 0 to 5 is 3, the integral from 0 to 7 is -10. Let's use those to calculate all these if possible. So the integral from 0 to 7 of 2 times f of x, well, that's just 2. You can pull out constants, right? So it's 2 times 0 to 7 f of x dx, which they tell us is -10. So 2 times -10 is -20. For part B, the integral from 5 to 7 f of x dx. Well, that's the integral from 0 to 7 f of x dx. And then minus the integral from 0 to 5. 0 to 5 f of x dx. Because if you do the whole thing and then subtract off the first 5, what you're left with is from 5 to 7. And so that's going to be -10 minus 3. So it's -13. For part C, the integral from 5 to 0 of f of x dx, so going in the backwards order, is equal to negative the integral from 0 to 5 f of x dx, which is -3. And then part D, the integral from 7 to 0, 6 f of x dx is equal to -6 the integral of 0 to 7 f of x dx, which is -6 times -10, which is 60. And then finally, E, the integral from 0 to 7 absolute value f of x dx. That one we can't do because in order to do this, we need to know when f of x is positive and when it's negative. So this is impossible. Impossible, because we need to know when it's above and when it's below the x-axis. Impossible, need to know more about f of x. Okay, so that's how we use properties of integrals. And so now the question is, what if we can't use geometry or properties to solve for the definite integral? We need to use the limit definition, right? So we need to use this definition right here. And so this is the limit definition for the right Riemann sum. And this is how we're going to calculate the definition. And I promise you there will be one of these, an easy one, but there will be one of these where you have to do this limit definition to define the area on the exam. And so I will do this one very carefully, but that's the idea. So the idea is I do the right Riemann sum for this guy on the interval 0, 2, and I want to take the limit as n goes to infinity. And so first thing, find delta x. What is delta x? Well, delta x is equal to 2 minus 0 over n. So it's 2 over n. That's delta x. And then, so the Riemann sum, the right hand, so R sub n is the right hand Riemann sum with n rectangles. What's that going to equal? It's the sum from k equals 1 to n f of x sub k star, but x of k star, we know what it is. It's f of a, which is 0, plus delta x, which is 2 over n times k, right? Because that's going to be the kth point. And then times delta x, which is 2 over n. And so now we plug this guy into this function. So this is the k equals 1 to n, and that's 2k over n cubed. So 2k over n cubed plus 1 times 2 over n. So that's the right Riemann sum. And I could simplify this out if I wanted to. What's that going to be? This will be the sum from k equals 1 to n. That 2n will distribute. So it'd be what, 16 k to the third over n to the third, no, n to the fourth. N to the fourth plus 2 over n. So that's what Rn is. So that's the right Riemann sum. So right hand Riemann sum with n rectangles is that. So copy. So that's what that is. And so now what we need to do is take the limit as n approaches infinity. So thus the integral from 0 to 2 x cubed plus 1 dx is equal to the limit as n goes to infinity of that, which is sum from k equals 1 to n, 16k cubed over n to the fourth plus 2 over n. And so we need to get rid of this k and this sigma using formulas. And so let's do that. So this is the thing. So this is what we're going to play with now. So how are we going to simplify that? We're going to use sigma notation rules. And so this becomes the limit as n approaches infinity. And then this is going to be 16 over n to the fourth sum from k equals 1 to n, k cubed, and then plus 2 over n sum from k equals 1 to n of 1. And so remember what these formulas are. I actually don't remember what that formula is, but I can paste it. So that is the formula. So that's the formula I'm going to plug in for I'm going to plug that guy in for k. So plug that in for k, or sorry, for that whole thing, not just for k, but for the sum. So that's going to get plugged in for that. And then this one is just equal to n. And so what's this going to equal? So equal to the limit as n approaches infinity of 16 over n to the fourth. And then replacing that with n squared times n plus 1 squared all over 4, and then plus 2 over n times n. And then what will this simplify to? This is going to be the limit as n approaches infinity of that cancels with that and gives a 4. So it'll be 4 and then n squared times n plus 1 squared, which is going to be n to the fourth. Maybe I should do it like this. Let me do it like this. 4n squared times, then this is n squared plus 2n plus 1 all over n to the fourth, and then plus 2. So if you take the limit as n goes to infinity, it really only depends on the lead term. So this is going to be the limit. So n approaches infinity of 4n to the fourth plus 8n cubed plus 4n squared all over n to the fourth plus 2. And that limit is just going to be, because it's n to the fourth over n to the fourth, and those are all smaller, those go to 0. And so it's just going to be 4 plus 2. It's equal to 6. So thus, the integral from 0 to 2 of x cubed plus 1 dx is equal to 6. That is a lot of work to calculate that exact area. We're going to learn a much easier way. So here's a preview of what we're going to do next time. But the fundamental theorem of calculus tells us that this is actually equal to 3x, x to the fourth over 4 x to the fourth over 4 plus x evaluated from 0 to 2. If you plug those in, you get 4 plus 2 minus 0, which is 6. And so that's a much easier, and I'll show you what all this is. So this is later. This is 5.3. This is 5.3. So preview, 5.3 preview. And so that's much easier way to calculate it. This whole limit definition is kind of a pain in the butt, but just like when we were learning the definition of derivative, it's important that you know it. And so there will be one on there. So there it is. That's everything you need. Good luck. Take care.